Okay, so let's talk about Unit 8, Worksheet 4, Quantitative Energy Calculations and Energy Conservation. Now, the first 6 problems on this worksheet are a chance to get practice using our equations for the different ways that energy can be stored. Problems 7 through 10 take advantage of our LOL charts, those energy bar charts, to first qualitatively show how energy is stored at an initial position, and then how it is stored at the final position. Then we can use the conserved energy equation to, well, quantify the amount of energy that is stored in different accounts, both before and after. I'm going to start with problem number 10 as an example problem on how we can use those LOL charts to help us to solve these problems. So problem 10, the moon could be an ideal spaceport for exploring the solar system. A moon launching system could consist of a magnetic railgun that shoots items into moon orbit. How much energy would be needed from the railgun to get a 10,000 kilogram capsule into an orbit 100 kilometers above the moon's surface? The moon's gravitational field strength is 1.6 newtons per kilogram, and the orbital velocity for this altitude is 1,700 meters per second. Hint, put the railgun outside of the system. Okay, so when we're seeing problems that are this big, it is probably going to be a really good idea to, one, draw a picture or a diagram to make sense of what the problem is really representing, and also keep in mind what the problem is asking us to solve for. Now, looking for what the problem is solving for, that's going to be looking where the question mark is. So that question is going to be how much energy would be needed from the railgun to get a 10,000 kilogram capsule into an orbit 100 kilometers above the moon's surface. So we'll need to keep that in mind. By the time we are done with this problem, we should be able to answer this question. What is the amount of energy from the railgun? Now, I'm going to draw the diagram to make sense of what's happening here. So underneath this, I'm going to draw a picture-perfect version of the moon. Right there, that is the moon. It's perfect. So we're going to have a moon launching system that could consist of a railgun. I don't know exactly what that's going to look like, so I'm just going to represent it with a giant rectangle on the surface of the moon. The surface of the moon, by the way, is what I can define as my height of 0. How much energy would be needed from that railgun to get a capsule into orbit? This can be our capsule, and it is orbiting around the moon. We know the mass of that capsule is 10,000 kilograms. That is right there in the problem. We know it's going to have an orbit 100 kilometers above the moon's surface. So it has this height of 100 kilometers, or to put that in the correct unit of measure, that's going to be 100,000 meters. The moon's gravitational field strength is 1.6 newtons per kilogram. So the G on the moon is 1.6 newtons per kilogram. And the orbital velocity is 1,700 meters per second. It's probably safe to assume that before this capsule gets launched into space, it's going to start off with a velocity of 0 meters per second. The reason why this is going to be so important is so that way we can define our two positions. I'm going to say that right here, this is going to be position A before the capsule has been launched. And then up here is going to be position B after the capsule has been launched and it is in orbit. So if I'm looking at position A for my LOL chart, which I can use to fill out to figure out what equation I need to use, the velocity is 0, so I'm not going to have any energy stored in its kinetic account. The height is 0, so I'm going to have no energy stored in its gravitational account. Now, my understanding is capsules are not really elastic, so I'm not going to be having any energy stored in its elastic account, and I typically don't start off with thermal. Now, the very first thing I probably should have done was identify what the system was. Our hint is to put the railgun outside of the system, so it's outside of our system. So that means inside our system has to be the capsule and the moon. And I'm just going to confirm real quick at position A, yeah, the capsule isn't moving, so no kinetic. The capsule is on the surface of the moon, so EG is 0, no height. Capsules are not elastic, and there's no thermal at the beginning. Okay, now I can move on to position B. At position B, it is moving. It's moving 1,700 meters per second. So I'm going to have some amount of energy represented in its kinetic energy account. I'm just going to go with 2 bars. I know it has an altitude of 100 kilometers or 100,000 meters, so I'm going to say I have 2 bars of energy in its gravitational energy account. While it's up in space, I don't think the capsule will become elastic, so I'm going to say that's 0. And then I'm not going to say there's any thermal, because when objects get launched, traveling through the atmosphere, the air can be slowing it down. But if this is going to be on the moon doesn't have an atmosphere, so we're not going to have any air resistance. So I'm not going to have any energy stored in the thermal energy account. So right here, I'm going to see if my energy is balanced at position A and position B. They're not. I have 0 bars of energy represented at position A, but I have 4 at position B. I can't balance them just by adjusting the quantities before or after, because while I could reduce the amount of bars that I have stored at the end, I can't reduce it to 0 because, well, the capsule is moving, so it has kinetic energy storage, and it is above a height of 0, so it has some energy stored in its gravitational account. That means that energy has to enter our system to account for that energy at the end. I have 4 bars at the end, so I'm going to have 4 bars entering our system. It enters our system via working. So when it comes to my conservation equation, I'm going to have the work that is done on our system is equal to our, ways that energy is stored at the end, our kinetic energy and our gravitational energy. All of the energy that is accounted for at the end of this problem came from the amount of energy that entered the system via working. Oh, actually, I suppose now's probably a good time to point this out, that this working right here is going to be the same thing as the amount of energy from our railgun. And that is actually what we're looking for in this problem. So if we can quantify our EK, which is 1/2 times our mass times velocity squared, and our EG, which is going to be mass times g times the height, and I add those together, I can actually quantify how much energy was supplied by the railgun. This is where I'm going to use all of those variables we wrote down at the beginning of this problem. And just to make myself have a bit more space, I'm going to be using all of the space on the bottom of my actual page. So my E for the railgun is equal to the 1/2 times the mass of the capsule, 10,000 kilograms, times the velocity, 1,700 meters per second. All of that gets squared. Plus the mass of the capsule, 10,000 kilograms, times the gravitational field strength on the moon, 1.6 newtons per kilogram, times the height, which we're saying is 100,000 meters. So I'm going to break this down into 2 parts. The first part is going to be all the ways that the energy is represented with our kinetic account, and then all the ways it's associated with our gravitational. So when I plug this into a calculator, 1/2 times 10,000 kilograms times 1,700 meters per second, all of that gets squared, I end up with a massive number. My calculator spits it out in scientific notation. I get a number of 1.445 times 10 to the power of 10. Now, kilograms times meters squared per seconds squared is going to be joules. I'm going to add that to the amount of energy associated with the gravitational account. 10,000 times 1.6 times 100,000 gives me a much smaller number. Still in scientific notation, I would get a number that is 0.16. 0 times 10 to the 10th power. Now, my calculator actually gave it to me in 1.6 times 10 to the 9th power, but I rewrote it in times 10 to the 10th power, so that way we could compare these 2 ways energy is represented. Our gravitational is 0.16, whereas our EK is 1.445. So we have almost 10 times as much energy represented in our kinetic account than we do gravitational. I can do that comparison because they have the same order of magnitude represented by the exponent there. When I add these together, I can actually quantify the amount of energy that was provided by the railgun. That will be 1.605 times 10 to the 10th power joules, and that is the energy from the railgun, which is what we were looking for in this problem. But the last thing that I'm going to do now that I have quantities for my EK and EG is I'm going to adjust the scale of my LOL bar chart. Because I know I have 10 times as much EK as I do EG, I want to represent that qualitatively as well. So I still have some EG, but I don't have a whole lot. So I'm just going to put a small amount. Whereas for my EK, I have way more of it. And I'm just going to qualitatively try to show that I have maybe about 10 times as much. That's the last thing that I did with my LOL chart to make it make more sense based on the amount of energy that is represented in the kinetic and gravitational accounts. But those two counts, when we put them together, end up with what we're solving for in this problem, the amount of energy that must have been provided by the railgun.